We will wait for 5 more minutes for others to join. Good evening all. Am I audible? Hello? Okay, so let's start. So I am here to conduct this interactive live session on week 3 videos. So we'll start. So I'll first give some hello. Okay, so first I'll give the topics covered in week 3, so that will be helpful for you to get an idea of those topics. So the first topic, Hello. Sorry for the interruption. I lost network connection. So we'll quickly go through the recap of week 3 videos. So first we had rotational homography. Hello, am I audible? Just reply in chat.
Yes, ma'am.
Okay. So first topic is rotational homography. Then sir explained research challenges. Then he explained about real aperture camera. Then about space variant and space invariant blur. Then linearity and space invariance of lens. Then 2D convolution introduction. And the next topics will cover 2D convolution. So we have first one is rotational homography. So homography is what? Actually we have an image here. We have an image I1 and image I2. Then we have a flower here, but in the image 2 the same scene, but the flower will be at a different position, which is captured by a different camera setting. Or if we are capturing it with some rotation or translation of the initial camera, we'll get I2. Then we have to relate this I1 and I2 using some homography H. That means every point in I1 should map to I2 points using the homography matrix H. Then you can write the second coordinates x2, y2, 1 is equal to h into x1, y1, y. This is known as homography. So H can be anything, right? So we can rotate the camera or translate the camera. So in the last week videos, sir explained like a point in second image can be written as the product of this matrix. What is that matrix? H is equal to K into R plus T n transpose by D into K inverse. So this H is for general motion. There can be translation as well as rotation. So rotational homography considers, so this general homography equation, the condition is that the scene should be planar, that is D. Here we have one depth term D here, so that should be the same for every point. So we have to consider a planar scene. On that only we can apply both the rotation and the translation. So if we have a translation of the camera, that is if we are rotating, your camera is here and you are translating to another position to get another image I2, then if the two images are connected using a single homography, then the condition should be the scene should be planar. There should not be any variation in the depth. Then only we can write it using a single matrix H. Okay. So in rotational homography, it is stated that we have only rotation, no translation is there. So how will we write? General H is written as K into R plus T n transpose by D K inverse. So for rotation only, we don't have this T is equal to 0. Then what will you write? H is equal to K R K inverse, right? But this equation doesn't have any depth. No, there is no depth factor here. So depth can be anything. So for pure rotation means we have a camera like this, we will rotate it. Rotate it means we will rotate the camera like this around any axis. So that rotation need not have, there should not be any condition that the scene should be planar. There can be depth information also. Then also we can represent it using a single H. So say we have depth seen like this. If we are using a translation only, we cannot represent it using a single H. But if we are using this rotation of the camera, then we can represent it using a single homography matrix H. Okay, so for rotational homography there can be some depth difference. So world can be 3D, but in the case of translation, the plane, the world should be a single plane. There should not be any depth difference. So the question 1, I'll pose the poll here. You can answer. So which of the following options is correct for two views to be connected using a single homography? First one is world should be planar and there can be translation as well as rotation. World can be 3D but there should be only rotation. B, world should be planar and there can be translation as well as rotation. World can be 3D but there should be only translation. Third option, world should be always planar irrespective of whether there is only translation, only rotation or both. You can answer based on what I explained the last slides. So poll is live now. Anybody can answer in chat also. Our aim is to connect two images using one single homography matrix H. Okay. So if we have translation, there should not be any depth difference. So scene should be planar. If we have only rotation, there is no term of D. So there can be depth difference also. So the scene can be 3D. So we are constrained either camera motion or world. Okay. So camera motion can be translation and rotation. Then the world should be, if there is a translation, world should be planar. Planar means what? A distant view. Okay, where there is no depth difference. So if the camera motion is only rotation, the world can be 3D also. Even if it is 3D, we can represent two views using a single homography. That is the concept. Okay, so the answer will be A. World should be planar and there can be translation as well as rotation. World can be 3D but there should be only rotation. Okay. And the next question is about real aperture camera. So after going through that pinhole camera model, we went through what real aperture camera, where we have a lens here. So the question is, what is meant by the working distance of a camera? So there are many terms regarding one camera or working distance of a lens. So what should be working distance? Anybody know? So I launched the poll. If anybody knows, you can answer. So working distance is what? So we want every point to be focused in the image plane, right? This is image plane. So we want every point to be focused on the image plane. But due to depth difference, this point A may be focused here, but this B will not be focused here. Okay, this B point is here. That won't be focused here. So for A, there will be a single point that is known as focused point. Some one point is in world one point is in image plane, so that is purely focused. But in the case of point B, it won't be focused in the image plane, but we will get a blur thing, right? So a single point will be blurred like this on the image plane. So the question is, what is working distance? So the working distance means, so in this case, this is the working distance. What is working distance? The distance from the lens center to the world for the object to be focused in the sensor plane. So at what distance we have to place our object or the point, so that that point should be focused on the image plane. So that is known as working distance. But in the case of this point B, it is not focused on the image plane, right? So that is not the working distance. Working distance is the distance from the image center to the lens center to the point A. Okay. So the answer is C, distance from the lens center to world for the object to be focused in the image sensor plane. And next is the concept of depth of field. Okay, so depth of field is explained in the lectures. So what is depth of field? So in some of the images we could see some blur in the image, and in some part of the image there won't be any blur. So here in this picture we can see that this portion that is just behind this shelf. So this from this point to this point, there is the points are clear, right? So that distance is what is known as depth of field of the camera. So and the backward points are actually blurred, right? So that depth distance is known as depth of field. So how much distance we could see uniform sharpness in the image, that is known as depth of field. So here are some of the examples. Here we could see that in this image, in the first image, we have this much sharpness, right? And after that there is blurriness. But in the case of second image, we could see a sharpness from here to here. So depth of field is increased. For the third image, depth of field is high. So almost all the image portion are looking sharp for the third image. So this is known as depth of field, but ideally speaking, only one point will be focused on the image sensor plane, but some of the neighboring points also are seen to be focused but not exactly focused, but we could get a feeling that those points are actually sharp points. Okay, so that is known as depth of field. So depth of field is a distance in the 3D world. Okay, so here you can see that one camera is here, one object is here, and the object is placed in the on the world. Okay, so before some portion and after some portion, they are actually blurred on the camera, on the sensor plane. But that flower portion and some portion just before the flower and after the flower, they are also sharp. So we can say that the whole length is known as depth of field. Okay, then depth of field is dependent on focal length of the camera, aperture size of the camera, then focus distance means distance of the object. Okay, so there are many explanations in internet, you can search. So here the first figure, it is seen that if the distance, so this right, that face images are actually world points. Okay, So these are actually world points. So if the distance from the world point is increased, then depth of field is also increased. That is one condition. So if the object depth of field is increased means not only the face is sharp, but also some of the portions just before the face and after the face will be focused on the image sensor. So we can see we can say that if the distance of the object is increased, depth of field is also increased. Okay. Then the next case is aperture. Aperture is what? So the area of the lens through which light enters. So here the aperture is less. Okay. But here the aperture is high. Okay. So if the aperture is less, for the second case, the depth of field is high. Okay. So aperture, as the aperture size decreases, depth of field will be increased. So this is the next case. Then regarding focal length, we can see that if for the lesser focal length, depth of field is increased. So in the first case, we can see that what if the distance is more, for the if the distance of the object is more, then the depth of field is more. Then if the aperture size is less, then depth of field is high. Then the focal length, if the focal length is less, then also the depth of field will be increased. So the question 3 is choose the correct option. So I have already explained the terms and the relations. You just answer. So depth of field, choose the correct option. Depth of field increases if the focal length increases, aperture size decreases, and object distance increases. Second option, depth of field increases if the focal length decreases, aperture size decreases, and object distance increases. So depth of field increases if the focal length decreases, aperture size increases, and object distance increases. So I have launched the poll. If someone can answer, just answer on the poll. So we can say that if the in the three option, depth of field increases, then object distance increases. Then the case is that if the focal length increases or decreases, then aperture size increases or decreases. So here if the focal length is decreases, depth of field increases. So if the focal length decreases, depth of field increases. Then in the first image, so in the second image, if the aperture size reduces, depth of field increased. So this one, right? So the answer is B. Then the next question, which of these following statements are true regarding pinhole camera and real aperture camera? So in the lectures, there is a comparison between pinhole camera and real aperture camera. So what was that? Regarding blurriness. Okay, so pinhole camera focuses every world point irrespective of the depth, but real aperture camera has lens, so that will focus some of the points depending on the depth. Okay, as I have already explained that the green point is not being focused on the image plane, so it depends on the depth. So real aperture camera depends on, first of all, can you answer this question? Real aperture camera and pinhole camera. First option is real aperture camera yields focused image always, but pinhole camera gives blur. Second option, pinhole camera yields a focused image always, but real aperture camera gives blur. The third option, there will not be any type of blurs in pinhole camera. So the thing is that this is a pinhole camera. So this is the image plane. So every point on the world will be focused on the sensor plane using a pinhole. Okay, the thing is that we have to increase the exposure time, that's all, to get sufficient light to the image sensor. So this is irrespective of the depth irrespective. Okay, so pinhole camera always focuses world points irrespective of depth, but in the case of real aperture camera, as I have already explained, one lens is there that will focus some of the 3D points only. So it depends on the depth. So the first option is real aperture camera yields a focused image always, but pinhole camera gives the blur. So that is the opposite thing. So that is wrong. Pinhole camera yields a focused image always, but real aperture camera gives blur. So that is correct. Then the next option, there will not be any type of blur, defocus or motion blur in pinhole camera. So in pinhole camera we can say that there is no defocus blur. Defocus blur is depending on the depth. So some of the depth portions will not be focused and some of the portions will be focused. That is defocus blur. Defocus blur will not be there in pinhole camera, but if there is a motion of the world, that is if the world points are moving or if the camera is moving, so light from other points also will fall on the image plane, right? So there can be motion blur in the case of pinhole camera. So the third option is also wrong. So there will not be any type of blur, that is wrong. There can be motion blur in pinhole camera. So the only the second option is correct. So the answer is what? B. Pinhole camera yields a focused image always, but real aperture camera gives blur. And the next question is, identify the type of blur in the following images. Motion blur, defocus blur, space variant blur. So in the first image, some blur is there. So what type of blur is that? Whether it is motion blur? You can answer in the chat box. First one, A. Just type A and what blur is there. So whether it is motion blur, defocus blur or space variant blur. Okay, so A is defocus blur. Is it defocus blur? Okay, there is a defocus blur also. Okay, what I meant is just name 3 blurs. Okay, B is defocus blur. Yes. So what is space variant blur? C is motion blur. That is also correct. C is motion blur. That is paka. Then B is defocus blur, and the A is also a defocus blur, but it is a space variant blur also. Space variant means on the image at every position there is different blurs depending on the depth. Okay, so that is known as space variant blur. So the first one is space variant, second one is defocus blur, and third one is motion blur. And defocus blur, okay, so the option could be like motion blur, space invariant blur and space variant blur. Okay, then question 6. So it is explained in the lectures. So I have explained that if you have a 3D world like this, and if you have a lens like this point A will be focused here, but this point B won't be focused here, but we'll get a circle, okay, as a blur. So what is the value of that blur radius? So that is already derived in the lectures. Can anyone say like what is the equation for that blur radius? What is the equation for that blur radius? So that will definitely depend on depth, right? Depth means d means how much distance is the object from the lens. So and d will be there, then working distance will be there, then r0 is the lens radius. Okay, so user is the distance from lens and the image plane. So the equation is b rb is equal to r0 u0 into 1 by omega d minus 1 by d. Okay, where omega d is the working distance. Working distance I have already explained, which is the distance from the image lens center, so that the point will be focused on the sensor plane. Okay, so the next question is, what will be the blur radius if the object is at a distance of working distance from the lens? So the equation for blur radius is r0 u0 into 1 by working distance minus 1 by d. So can anyone answer? Just substitute, that's all. So if the image is at the working distance, that is the object distance is d, right? So if that object is at working distance, then what will be rb? What would be the blur radius? We have already said that if the image is placed at the working distance from the lens, then there won't be any blur. So blur radius will be what? If there is no blur, there won't be any blur radius, right? Or just substitute here. What? Here in this case, the depth from the lens is working distance. So you will get r0 u0 into 1 by working distance minus 1 by working distance. What will be that? 0. That is, if the object is placed at the working distance, there won't be any blur. So rb will be 0. So the answer will be C. Okay, then the next one is, okay, lens is linear space invariant. So we have a lens here. Okay, so for every intensity I will get some either a focused point or a blur radius. Okay, so generally I draw it like a blur radius. Okay, g1. So first one is linearity. Linearity gives that if you are giving an intensity I1, then you will get a intensity at the image plane like G1. If you are giving another intensity I2 at the same point, then you will get not at the same point. If you are giving another intensity I2, then it will give an intensity at the image plane G2. Then if you are giving I1 plus I2, that is, if you are adding two intensities and you are giving to the lens, that lens should give G1 plus G2. So that is a linearity concept. And if the world is planar, we can give same shift to all the points, right? So if you are giving I1, then it will give G1. Then if you are giving a shifted version of I1, then that will give a shifted version of the image. So this is the space invariant property. So lens is space invariant, linear space invariant. Okay, so I haven't added any question there. Then question 8, which of the statement is true? So this is regarding, professor just started convolution. So that topic contains some Toplic matrix and circular matrices. So every convolution can be written using this multiplication with Toeplitz matrix, and the circular convolution can be written using the multiplication using circular matrix. So can you identify which one is Toeplitz matrix and which one is circular matrix? So Toeplitz matrix will have a form like the diagonal elements will be the same. So this element, these elements are the same, right? But in the case of circular matrices, every row will be a circularly shifted version of the previous row. Okay. So circular matrices are also Toeplitz matrices, but their the second row will be the circularly shifted version of the first row. So t minus n minus 1 comes here, and t0 will go here, 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 and etc. So which of the following statements are true? A is Toeplitz matrix and B is circular matrix. So that is the correct answer. And the next question is, verify that circular matrix is normal. So what are normal matrices? Normal matrices are A transpose is A transpose A. A transpose is equal to A transpose A is the condition for normal matrices. So circular matrix is how we can write A B C shifted version, B A C A B, then B C A. So this is a circular matrix. So just verify that A transpose is equal to A B C C A B B C A into A transpose A B C C A B B C A. Then you will get A square plus B square plus C square, AC plus BA plus. Okay, then you will get a 3 by 3 matrix. Then you just try A transpose A also, then you will get the same matrices. Okay, so that gives the verification of this normality. So the circular matrix will be normal. So this concepts will be used in the next week videos for 2D convolution to get the output of that image. So if you are convoluting two 2D signals, will get one output. So for that portion, this normality concept should be used. Then comes to our lab assignment 3. So I'll just explain how can you do this assignment, lab assignment 3. So the assignment is on mosaicing. Okay, mosaicing is what? Stitching these 3 images. So these 3 images are already given in the question. So we can't just join these 3 images, right? That can't be done because there are overlapping position here and here also. So we can't just stitch those images one by one. But so what should we do? First step is you have to find correspondence points between 2 images. Correspondence points means what? So you know that this building has one point here, this red point here, and in the second image you have the same building and the point can be marked here, right? So these points are known as correspondence points. So between 2 images there can be different correspondence points, and another correspondence points I will draw this building point and this building point. So which algorithm returns this correspondence points? So that code is already given to you, shift. So shift function will return the correspondence points. Means it will give the correspondence points like it will give you a set of points like in image 1 it will say that 1 comma 1 corresponds to image 2's 20 comma 20. So that information will be returned from the shift function. Then if you have this correspondence points, you can pass a set of, so you will have a set of 100 point set. You will have that 100 point set, you will have to pass through this ransack algorithm. Okay, so ransack algorithm, what ransack algorithm will do, last lectures ransack algorithm is there. So it will return 100 pairs of points, but you are not sure whether the shift returns the correct points. Otherwise your homography will be totally wrong if you are choosing wrong points. Okay, so say the shift returns this point corresponds to this point. So it is not sure that shift will return 100% correct point. So that green points are not correct points, but shift returns that point also. So you cannot guarantee that shift returns good points only. So by using 100 points, you have to find out which all points will give the proper homography H. So for finding H, so okay, so for finding H, you will need only 4 point correspondences. Okay, so that is already discussed. So this is already described, so explained in the last homography classes. So if you have H11, H12, etc., H33, this is your homography points. And if you have 1 point correspondences, you can write 2 rows here, and you have to equate that to 0. So like that, if you have 4 point correspondences, you can write 8 rows here. So from that you will get H1, H12 up to H33. So you need only 4 points, but shift returns 100 points. Then how can you ensure that this the 100 points are correct, or how can you get the correct points? That algorithm is known as ransack. That is already explained in the last lectures, and I have already explained the last live session also. So it will return a good H. Okay, so that H will be found out by using good points only. So this ransack will give return best H. Okay, ransack will return best H. Okay, then in ransack there can be some, so in ransack there will be one function also, find homography function, that will be used to find out this H, and that will be refined over iterations. Okay, so that find homography is a function inside ransack. So to that function we have to pass 4 point correspondences to get the H. Then that will be refined over iterations. So ransack will give the best H. Then that best H, so you will have to find out H between image 1 and image 2. Then you will have to find out H between image 2 and image 3. What is H actually? It is a homography between two images. So every point in image 1 will be connected to the image 2 elements by using a single matrix H. That is known as homography H. So you will get H between image 1 and image 2, H between image 2 and image 3 using ransack algorithm. So that homographies you will have to pass through this mosaic function along with the images to get the mosaiced version. Okay, so for that you will have to map image 1 to in the orientation of image 2, then image 3 to in the orientation of image 2, then you have to stitch the 3 images. So the whole thing is in the mosaic function, the fourth function. So for the transformation we have transform function, then bilinear interpolation is used to get the target to source mapping. So the steps are: read the first 3 images first, then find the correspondent points between image 1 and 2 using shift, and image 2 and 3 using shift. Okay, but that shift points won't be correct. So you have to use ransack to find the best H21 and H23. H21 is the homography between image 1 and 2. H23 is the homography between image 2 and 3. Then you have to then you have to select one full canvas for all the images to be fitted on a particular canvas. So say image 1, 2, 3 are having a size 100 by 100, then you have to take a width of 400 size for all the images to be fitted here. Okay, so first take a canvas here, then define a translation so that image 2 will be shifted to the center of the canvas. So you have to take one homography which contains only translation so that image 2 is at the center of the canvas. Okay, so that translation homography is known as offset. So in the code it is given that offset. Okay, offset is a translation homography to shift the image 2 to the center of the canvas. Then you have to apply H21 and offset. H21, what does H21 do? H21 will shift image 1 in the orientation of image 2, and along with that we have to apply offset also, so that shifting to the image 2 orientation and then shifting to the center of the canvas. So both will done by using offset into H21. Then offset will be used for shifting image 2 without any transformation. Then offset into H23 is used to shift image 3 in the orientation of image 2 and the offset to the center. Okay, so these three homographies we have to pass through our mosaic function. Then that function will stitch all the images together big image. Okay, so this is the assignment 3. Okay, if you have already gone through this assignment, it will be easy for you to ask any questions and all. So be prepared and come for the interactive session so that you can answer, you can question me and I can answer, so that it will be helpful for you. Okay, and if you have any question you can ask now.